Welcome to week 2 of our class on differential equations 162.04. We're on to lecture 5 now, and in this lecture we're going to I'm going to introduce a method of solving first order linear ODEs using something called an integrating factor. Okay, so this first order linear ODEs we touched on at the end of lecture 4. So you may like to refresh your memory on that by rewatching the last 10 minutes or so of lecture 4. And secondly, we're also going to introduce the existence and uniqueness solution, or theorem rather, for first order linear ODEs. Okay, so we previously have written down a theorem on existence and uniqueness for general first order ODEs, but now we're going to have a specific one for first order linear ODEs. And secondly, we're also going to introduce something called transient terms. Okay, so consider this first order linear ODE in the standard form. So recall the standard we introduced last time in lecture 4. The standard form, the coefficient in front of dy by dx is 1. There's no other function or any other multiplier in front of this derivative apart from 1. And if we write in such a way, we have a function, a coefficient p here, which of course only depends on the independent variable x. And on the right hand side we have a function f of x, which again only depends on the independent variable. And again, recall, if f was 0, we called this a homogeneous first order linear ODE. Otherwise it was a non-homogeneous first order linear ODE. Okay, so the technique we're about to learn is called using an integrating factor. So we're solving this first order linear ODE using an integrating factor. So this method only works for first order linear ODEs. So the idea is we want to try and find a new function which we're calling mu, which itself is a function of x, which when we multiply, we can multiply it to the linear ODE. So term by term here, we can multiply dy by dx by mu. So here we've got mu times dy by dx. We can multiply p times y. We can multiply py times mu as well. So here we have mu times p times y. And then we can multiply the right hand side, f of x, by mu as well. So we got mu times f here. Okay, so at the moment all we've done is multiply everything by mu. It's a completely legitimate algebraic operation. The trick to this integrating factor method though is that we want to choose a really specific value of mu. Okay, we can choose any mu that we like, really, but if we're clever, we're going to choose a mu which is going to simplify our system. Okay, so we want to choose mu of x so that the left hand side of this equation here is exactly equal to the derivative of mu times y. Okay, so in other words, this left hand side here, I want this left hand side of this equation to be equal to d by dx of mu times y. Okay, and you'll see why I want this in a minute. So if I rewrite that last equation there, the left hand side mu times dy dx plus mu times p times y equals the derivative with respect to x of mu times y. I can expand this right hand side using the product rule, right? So keeping, for example, I can't remember which order I did it. Okay, I did. Firstly, I kept mu constant and took the derivative of y, so I get mu times dy dx. And then by the product rule, I have a second term plus, keeping y constant now, du mu by dx times y. Okay, and we can immediately see that some of these terms on the left hand side and the right hand side of this equation are going to cancel. So we have a mu dy dx and a mu dy dx here. So we can immediately subtract that term from both sides of the equation. And I also have a multiplying factor y, which I can divide through by y and cancel out, right? So I can eliminate these terms that are covered in red, and I can divide through a factor of y here in blue. So I get left with mu times p, this function p, equals d mu by dx. Oh, okay, and so the thing to notice here is that you can think of this mu of x here, d mu of x here, as being some new variable here. And if you do that, you can see that this is actually a separable ODE, which we've looked at in the last class, lecture 4. So I can divide the left-hand side through, sorry, the right-hand side through by mu of x to get all the mu of x, all the mu terms on the left-hand side. I can multiply by dx to get all the x terms on the right-hand side, and I get d mu over mu equals this function p from the original ODE times dx. And of course we can integrate both sides of that equation. The left hand side, we're just going to have the logarithm of mu. The right hand side, well, this is going to depend on the specific problem, on the specific function that p is. So we get the log of mu equals this integral of p dx, and hence I can take the exponential of both sides and finally come up with some expression for this mysterious function mu. So if you remember none of what I've just said, just remember the definition of this integrating factor mu here. So mu is equal to the exponential of the integral of p, the function p, with respect to dx. Okay, so how does this help us defining this thing called an integrating factor? Well, if I come back to the original ODE here, now armed with the fact that I know what mu is, again, I'm going to multiply each term in this ODE, this first order linear ODE, I'm going to multiply that by mu. The difference, so we did this before, but the difference now is that we know exactly what mu is. But I'm also going to use the fact that I said that this left-hand side of this equation had to be equal to the derivative with respect to x of mu times y. Okay, so d by dx of mu times y equals the right-hand side mu of f of x. Okay, so this is exactly the same as what we have previously done, but now I actually know what mu is, right? So I can multiply both sides by dx and integrate. So now I have sort of this new variable. I've got the differential of mu times y. So this is like some new temporary variable here, mu times y. The right hand side is just the straight integral of mu of x times f of x. Recall f of x is the right hand side of our ODE. Okay, the left hand side though, this is effectively saying we're going to integrate the number 1 with respect to the variable mu times y. And if you remember, whenever we integrate the number 1, then all we get is, for example, if we had the integral of 1 dx, then we would just get x back, right? But in this case, we have the integral of 1 d mu y. So in fact, the left-hand side is just going to be the integral of d mu y is equal to just mu times y. Hence, the solution to the first order linear ODE, dy by dx plus p times y equals f of x, is given simply by y is equal to 1 over mu times the integral of mu of x times f of x dx plus some integration constant. So where did this come from? Came from the previous page. Okay, well again, if I integrate this left hand side, d mu 1, integral of 1 with respect to d of mu times y, I get mu times y. The right hand side is the same but with an integration constant, plus c naught. I divide through by mu on the left hand side, so I just get y left on its own. So I get y is equal to this thing plus some constant divided by mu of x. So that's how I got this expression here. So again, recall that mu of x is this thing exponential of the integral of p of x dx. Do not forget the integration constant. It is very important in this case. And also note that this factor out front, 1 over mu of x, and when we can define mu of x, right? We have an expression for mu of x. this factor at the front is multiplying not only this integral, but also the integration constant. So this is why we cannot forget the integration constant, otherwise our solution will be wrong. If you remember nothing else from the last 10 minutes of this class today, just remember this slide. The solution to the first order linear ODE in the standard form here is given by y is equal to 1 over mu times the integral of mu times f with respect to dx plus some integration constant, where mu is this expression, the integral of the exponential of the integral, sorry, mu is equal to the exponential of the integral of p dx. So let's look at a couple of examples. Okay, well, this is known as the general solution to the first order linear ODE. So let's look at a few examples now. Okay, so the example 1 here, 1 over x times dy dx minus 2 over x squared times y equals x times cosine x. So this is clearly a linear first order ODE. Dy by dx here is linear, and there's no multiplying terms which it's not multiplied by any function of y, only of x, which is the independent variable. Y enters here linearly, and there's no y's on the right hand side, so it's clearly a linear ODE, but it's not written in the standard form, right? So the standard form says that dy by dx has to be just multiplied by 1, not 1 over dx. So I can multiply both sides of this, well, every term in this equation by x, right? And that will, if I do that, I get x over x is 1. So if I do that, I get dy by dx equals negative 2 over x now. So I've got 2x over x squared becomes 2 over x equals x times cosine x, so x squared cosine x. So before I could do anything, before I could apply this integration factor method, I first had to write this in the correct form, the standard form. So I can now easily identify the functions p of x and f of x. So p of x is just the coefficient in front of y. So that's clearly going to be negative 2 over x, and f of x is going to be the right hand side. So p of x is negative 2 over x, f of x is x squared times cosine x. Okay, so now I've got my differential equation in standard form. I've got my function p and my function f. I can therefore define my integration factor, right? Which is just the exponential of the integral of p of x. Okay, so in this example, p of x is negative 2 over x. So I get the exponential of the integral of negative 2 over x, which of course is just the exponential of negative 2 times the logarithm of x. Again, exponential and logarithm are inverse functions of each other, so they effectively cancel out. I can use log laws to take my negative 2 to being a power of this x, and therefore I end up with the mu of x is just quite simply x to the power of negative 2. So please convince yourself of the algebra there. Again, if you have any questions, let me know. So now I've come up with an expression for the integration factor mu of x. It's just 1 over x squared. Okay, and recall that the solution y is given by 1 over the integrating factor multiplied by the integral of mu times f plus the integration constant. Hence, in our case, our integration factor mu is x to the power of negative 2. So we got 1 over x to the power of negative 2 times the integral of the integrating factor is x to the negative 2. The right hand side of the equation is x squared cosine x, and we still have our integration constant here. So we have to add that in too. We can simplify this, of course, because x to the power of negative 2 multiplied by x squared is just going to be x to the power of 0, which of course is just 1. So our expression for y becomes x squared times the integral of cosine plus c naught. The integral of cosine, of course, is simply sine. So we get y is equal to x squared times sine of x plus x squared times the integration constant. So we must include the integration constant because there is an x squared reliance on that integration constant here. So congratulations, we've now solved our first order linear ODE using the integration factor method. So now we know two ways to solve ODEs. We know how to solve separable ODEs using the method we went through in lecture 4, and now we know how to solve first order linear ODEs using an integration factor method. Okay, well let's solve an initial value problem. Okay, so this IVP consists of this linear ODE, which is already written in the standard form, and this initial condition when x equals 0, y equals 40. Okay, so we can immediately identify these functions p of, in this case, t. So the independent variable in this case is t. Maybe it stands for time, I don't know. Y is still our dependent variable. But the factor in front of y here, the linear term of y, is just 2. So our function p of t is 2. Our right hand side is still just a function of the independent variable, and it's just simply this 50 times the exponential of negative 10t. The integrating factor is the exponential of the integral of that function p, so simply the integral of 2, the exponential of the integral of 2. The integral of 2 is just 2x, so we get quite simply the integrating factor mu is equal to the exponential of 2t. Okay, and sometimes I write exp for exponential. Sometimes I write e to the power of the argument of the exponential. These are equivalent expressions. I just wanted to point that out. Sometimes I mix them up. Sometimes I use both ways of writing this in the same slides. So I hope that doesn't perturb you at all. But anyway, we have this expression for the integrating factor now. Mu is equal to the exponential of 2t. Our solution we know we can write as y is equal to 1 over, okay, well here I've written mu of x, and here I wrote p of x, right? But okay, there's a small mistake. It should be mu of t, f of t. Okay, well let's ignore my mistake for now, please. Sorry about that. Okay, so I can write this as 1 over the integrating factor, or 1 over e to the 2t, multiplied by the integral of the integrating factor, e to the 2t, times the function on the right hand side, f of t, 50 e to the negative 10t, dt, which is also missing here, I apologize, plus some integration constant. Okay, and I can obviously simplify this equation because I can add the arguments of these exponentials. So e to the 2t times e to the negative 10t is going to be, well, 2 plus negative 10 is negative 8. So I'm going to get e. I've also simplified the factor out front here. 1 over e to the 2t is simply e to the negative 2t. So that e to the negative 2t times this integral of 50 e to the negative 8t dt, which again is missing, sorry, plus some integration constant. I can integrate that fairly easily and find that e to our solution y is e to the negative 2t times negative 50 over 8 e to the negative 8t plus our integration constant. So therefore, bringing in this factor of e to the negative 2t, our solution is y equals negative 50 over 8 e to the negative 10t plus the integration constant times e to the negative 2t. So this is the general solution to the ODE, but of course we were given an initial value problem. We were given an initial condition. So we can find this integration constant by using this initial condition. So when x equals 0, y equals 40. Or sorry, I should say when t equals 0, y equals 40. So if I substitute in t equals 0 into this solution here, well, e to the 0 is 1, e to the 0 is 1, I'm quite simply going to get when t equals 0, y equals 40, so the left-hand side is 40 equals negative 50 over 8 plus c0, which of course means I can solve that for c0 and find that c0 is some fraction, some number here. Therefore, my solution to the initial value problem is is given as so here, where I've just replaced the integration constant C0 by the value we found using the initial condition. Okay, so just as a summary of the integrating factor method, firstly we have to say, is the ODE a first order linear equation? If no, then we're going to have to use another method. For example, if it's a separable equation, we can just separate the variables. But if it is a first order linear equation, then we can use the integrating factor method. We can go to point B. Okay, point B is, well, make sure that the ODE is written in the standard form. That is the dy by dx term, or dy by dt, or the derivative term, has a factor or a coefficient of 1 only. If it doesn't, then you may need to do a little bit of algebra to rearrange that equation. Thirdly, write down the functions p of x and f of x, where p of x is the factor multiplying the linear term, so the y term in the examples we looked at. F of x is the right hand side of the equation, which is only dependent on x, or let's say only dependent on the independent variable. Okay, and we can calculate the integrating factor using this equation here, the exponential of the integral of p with respect to the independent variable. Okay, and then we can finally solve for y. And y is given by this expression here, which we derived. Y is 1 over mu of x, assuming x is the independent variable, 1 over mu of x times the integral of mu times f dx, plus the integration constant C0. And please don't forget the C0, it's extremely important. The solution is wrong without it, in fact. And then finally, if the problem is an initial value problem, then we can use the initial condition that we're given to solve for the integration constant. Okay, so please go away and do some examples from the textbook, from the study guide. And again, if you're having any trouble, if you have any questions, please let me know. There are some questions in assignment 1 where you'll be asked to solve a first order linear equation. Okay, so now we know how to solve a first order linear equation. Let's look at a little bit of theory about first order linear equations. So recall that we had previously had an existence and uniqueness theorem for first order ODEs. So that previous theorem was for linear or non-linear ODEs. In the very specific case that we have a first order linear ODE, we have a second, or let's say a more precise existence and uniqueness theorem. So if we have this first order linear ODE, dy by dx plus p of x times y equals f of x, if p of x and f of x are continuous on some interval a to b, where a and b is just some numbers, and on this interval we have the initial point x0, then for any initial value when x equals x0 and y equals y0, then there exists a unique solution, which we're going to write as y of x, on this interval a to b to the initial value problem, the first order linear ODE and the initial condition. Okay, so again, this does look a little bit similar to the original existence and uniqueness theorem, but in fact this is giving us a little bit more. The existence and uniqueness theorem previously said we only guaranteed to have a unique solution on some rectangle in the region of the initial point. This is saying we basically have a solution wherever p of x and f of x are continuous on some interval, and it could be an infinite interval, in fact. So if the conditions of this theorem are met for first order linear ODEs, existence and uniqueness is guaranteed on the whole interval, not just some small region. Okay, well let's look at an example here. So dy by dx plus 1 over x times y equals sine of x. Again, a first order linear ODE here. We can identify these functions p and f. So p is the coefficient in front of the y, in front of y. So p is 1 over x. The right hand side, sine of x is equal to f of x. And we can see that 1 over x, so p equals 1 over x, is not continuous or not defined at x equals 0. Okay? So it's continuous for all x that are not equal to 0. Maybe this is a little clumsy way of saying it's not continuous at x equals 0, but it is everywhere else. Sine of x, no problems, right? Sine of x is always continuous for any value of x you plug into sine of x. Okay, so what does this tell us? This tells us that a unique solution to the initial value problem exists as long as the initial condition is not equal to 0. Okay, so we can have, if our initial condition lies in the range negative infinity to 0, not including 0, then we have a unique there exists a unique solution to this initial value problem on the interval negative infinity to 0. Or alternatively, if the initial condition was positive, so between 0 and infinity, not including 0, then there does guaranteed to exist a unique solution on the interval 0 to infinity. The only problem here occurs if our initial point x0 is equal to 0, and in which case we would have no guarantee of a unique solution. Okay, so I think the existence and uniqueness solution theorem for first order linear ODEs is slightly tidier than for general linear nonlinear ODEs. So to finish up this class today, I just wanted to define one further thing, which is transient terms of first order linear ODEs. So if we consider the initial value problem dy by dx plus y equals 4, supplemented with this initial condition x equals 0, when x equals 0, y equals 4. Again, clearly this is a first order linear ODE. We can solve using an integrating factor method, and well, maybe you might like to go away and convince yourself that this is the solution, and also that the solution is defined over the whole real line. This should be negative infinity to infinity. Okay, well, you might like to try this to make sure you get the same solution that I do. So the term in this solution here, y equals x minus 1 plus 5e to the minus x. This term 5e to the minus x, this is called a transient term. Okay, and the reason it's called a transient term is because as x gets larger and larger and larger, as x goes to infinity, this term approaches 0. As x gets larger and larger and larger, 5 times e to the minus some number that's getting larger and larger and larger. So in other words, we have the exponential of some increasingly negative number. If you recall how the exponential behaves, as the exponential approaches e to the negative infinity, the exponential itself approaches 0. And so, sorry, as x approaches negative infinity, e to the x approaches 0. So this term, as x gets larger and larger, this term becomes smaller and smaller and smaller, and in the limit it's equal to 0. So really it's called a transient term because it's only around, or only affects the solution for small x. The other term, x minus 1, well, this sticks around as x goes to infinity. This term just gets larger and larger. Okay, well, that's everything that we needed to cover today. If you have any questions, again, get in contact with me. Otherwise, I'll see you in lecture 6. Thank you.